Hi folks, you are already familiar with the LTSpice GUI and toolbox. In the last couple of episodes, you have become familiar with basic CMOS logic circuits. In this episode, we will construct a CMOS NOR gate using 4 monolithic PMOSFETs and NMOSFETs, where the PMOSFET has double the area of the NMOSFET for mobility balancing. We will apply pulsed waveforms shaped like square waveforms as the two inputs of the constructed NOR gate. The two square waveforms have different on-time and off-time to cover all the truth table combinations of the two input NOR gate. We will apply proper DC biasing and transient analysis to check the functionality and performance of the constructed NOR gate. So stay tuned, stay focused. Hey guys, welcome back. Last couple of episodes, we have covered multiple CMOS circuits. So you are very much familiar with the CMOS circuit construction. Today we will construct a CMOS NOR gate and we will be using 2 PMOS and NMOS. 4 of them are monolithic MOSFETs and we will be using the transient analysis to check the performance. And we will cross-verify using the output waveforms of this NOR gate. So without any further delay, let's begin. Here is our LTSpice window and we will click the new file icon here to open the dashboard for creating the schematic. Now first we will save the circuit, go to File, Save As, and here we will name it CMOS NOR gate. Then I click on Save. Here you can see that the file name is getting displayed at the topmost corner as I am highlighting. So we will be working on this particular file. Let me clear the screen. First I will go to the components here and I will go for the MOS4. This is the monolithic MOSFET as I have used in the previous CMOS circuits. And I will click and I will place. So there will be 2 PMOS. First PMOS is here, the second PMOS is here, and let me right click so that it vanishes. And now here I'll do a zoom out so that I can place more components here in this particular dashboard. I go again and click components. From here I will pick the NMOS4. Again this is a monolithic MOSFET as I have used in the previous circuits. I'll click place icon and I'll pick and place NMOS. And I'll right click to vanish this. I'll go and click the save button, that whatever schematic we have done so far is saved, and I'll again click the zoom out button once so that now I can place more things. We will need one load resistance, so I'll be clicking the resistor icon and I'll be placing it here where I'll be measuring the output across this. I'll right click to vanish it and then I'll go to the component. And from here, I will place voltage. So this will be the DC biasing voltage or VDD. I'll click place here and I'll place it here. I right click to vanish it. I'll add more voltage sources later. So let me now save the circuit and I'll do the interconnections here. First I go to this point, click, go upwards, then click here, then move right and go click here. And then I come down and I click here and I connect with. Again I click here, go to the right side, click here, go up and click here. I click this point and tie it up. I will click these 2 points together. I connected these 2 points. Next I'll do the further connection. I'll draw the ground line. So click here, go down, click here, then go rightwards and I click here, go up to the resistor point. Click here to connect it. Next I will click the ground and I will place the ground. I will go to the connection wire and I will connect this ground to this ground line. So our ground line is ready and now the NMOS I will connect them to the ground and these 2 substrates are tied down to the ground, that is VSS generally called. And here the basic MOS connections are done. Okay, so I'll go ahead and save the circuit. I'll continue the interconnection. I'll click here, go up and go up to this point. Okay. click here, come down, and I will connect with this. I click here, connect this too. I click here, connect this with this particular line. This point I connect, click, come down, go rightwards, click here, come down, and then I connect. I'll click here, come up to this point, go up to this point, move rightwards and connect with this point. Now, I think the interconnections of this circuitry is done. We are yet to connect two voltage sources. All the MOSFET nodes are connected. I'll click here, go up to this point, come down up to this point. I'll right click and vanish it. I'll place a voltage source here. I'll go here, the voltage, pick it, and I'll click here. Right click it to vanish it. Now I'll connect this voltage source, the ground line. Now I'll click here, start the interconnection, come up to this point, right click to vanish it. I will click the components, click on the voltage, I click on the place and I will place another voltage source here, right click to vanish it, start it interconnecting again. Here, come to the ground line. I'll do a zoom out, see the entire circuit. I'll click on save and I'll zoom in. So here we can see that we have all the nodes connected, and let me check whether any node connection is remaining. I think node connections are done. All nodes are connected and no nodes have been left over. So I'll place the pins here. First I'll name as A, which is input. Okay. Place it here. Again, I'll place another pin, B, input. I'll click OK. And this is B. I right click to vanish it. Now we will click the output pin, that is A, NOR, P. So this will be our output pin, and I click the direction output here. And I click here. Because across the load resistance, we will be measuring the output. Let me click on save. I will now one by one configure the placeholders. That means whatever we have placed so far are placeholders. We have to give them the actual values. So I'll start one by one. This is voltage 5 volt. And its name is VDD. Next, this will be V2 and V3. These are the two pulsed waveforms shaped like a square waveform. And I'll start configuring them. I right click, I go to advanced, then I click on pulse, and here I'll be giving the value. It is 0, then 5 micro, then 1 femto, 2 micro, 4 micro, and number of cycles will be 10. So let me check 0, 5, 2 micro, 1F, 1F, 2 micro, 4 micro, and 10. I click OK. So this is a pulsed waveform. Certainly this will be another pulsed waveform. This B input, right? I click on advance, go to pulse. Now I'll give the values. 0 is 5, this is 1 micro, then 1 femto, on is 1 micro, period is micro, and number of cycles will be 20. Let me check the values. 0, 5, 1 micro, 1 femto, then 1 micro, and 20. I click OK, and this is configured. Let me click on save. Now we will configure the MOSFETs. The PMOS has double the area of the NMOSFET. To do the mobility balancing, for that, we will keep the gate length same of all of these MOSFETs. We will vary the width, and that's how we will make the area double for the PMOS as compared to its NMOS counterpart. So here I right click, length will be 20 micro and width will be 100 micro. Click OK. In this PMOS will be 20 micro and this will be 100 micro. Click OK. For the NMOS, we have the same gate length 20 micro and we will have half of the width, that is 100 micro. Length is 20 micro, width is 200 micro. Now I will move to the rightwards and this resistance here, it will be 100k, that is 100 kilo ohms, and the resistor name here, it will be R load, that is the load resistance. So I'll go ahead and save the circuit. Now I'll do a routinizing of the entire circuit. Let me bring my marker pen. So this is VDD with 5 volts. This is the first pulsed input that is shaped like square wave input, and this is again the second pulsed input shaped like a square waveform, and these are the two pulse waveforms. This PMOS, NMOS, and this is the R load. This substrate is diode high, substrate is also diode high, substrate is diode low, this substrate is diode low. The basic thing, we have the ground connection properly done here, and we have pin output as A nor B, and here we have a input pin A and we have a input pin B. So I think we have scrutinized the circuit. The circuit construction is done, the schematic of the entire circuit and proper nodes are done. All the placeholders have received their values. Now I'll clear the screen and I will enter the SPICE directive here. I'll place .ic. Okay, I'll place it here, and next I will click again. I'll put a .pan command. I'll click OK. I'll put here. I click save. Now I will modify the tran. I right click and its dialog box open up. I'll give the values here. So the stop time will be 10 micro. Up to this we'll do the simulation, and the start time is 0 and data will be saved from this point. Time step is 1 nano, and you can see our transient command is getting constructed. So we have done the configuration of the transient analysis. I'll click OK and I'll click finally save. Now I'll go take the mandatory thing, view, then SPICE netlist. Here I'll scrutinize again. So here we have 2 PMOS, right? And here we have 2 NMOS, and I have done a mistake here. I have given 200. So this is M4. I have to rectify this. This is why I go ahead and do the scrutinization, because these kind of errors will be identified through the text. Here you can see the 2 PMOS has double the width, okay, and 1 NMOS is half the width and one is same as PMOS. So this we have to rectify. This has the proper resistance as load resistance. We have the VDD correct, and we have the 2 pulse waveforms. We have the MOS models properly, and here is the SPICE lib file from which the models are getting used, and here we have the transient. So we have to rectify the M4. So we'll close this and I'll go for M4. I'll rectify here. So this is 100 micro. I'll click OK. Now I'll go save the circuit. Again I'll go and view the SPICE netlist. So here you can see the 2 PMOS now has double the width of the 2 NMOS. These two are 100. I have rectified the mistake that have been done, and I suggest every engineer to do this kind of scrutinization, because mistakes can be there even when you are in a full concentration. Mistake can be introduced by a typo. Now I'll clear the stream. I'll close this particular SPICE netlist. I'll go here, save it, and now we are ready for the simulation. I'll click here on the run simulation button and we click that, zoom it a bit that I get the circuit a bit more prominent. I'll click save here. Now first here I'll go and click the A and see the waveform. From keyboard I will hit D. Again I go to this window and I get the voltage of E. You can see it has higher frequency, that means almost double the frequency of the first one. From keyboard I will hit B. So these are the 2 inputs we have captured here. Now I will go for the output pin. So here the output comes. Now let me verify the truth table for the NOR gate. Let me bring on my marker pen. So for NOR, only the 0-0 combination will have 1. We have 0 here and 0 here. We have 1 here. Rest of the all combinations, that is 0, 1 is 0. So 0, 1 is 0. 1, 0 is 0. And 1 is 0. So for NOR, only when both of the inputs at 0th level, the output is 1. So here we can see again this is coming when both of the input are 0, the output is 1. This is conforming to the NOR gate truth table. So we have constructed the NOR gate successfully, and here you can see up to this we have a truth table, and as we go further in this direction, the truth table combinations are repeating again and again through the wave. So let me clear the screen. So here we have constructed a CMOS NOR gate and verified its truth table using the output waveform. One final check is remaining. I'll go to the circuit, go to view, and then I'll check the SPICE output log. And here you can see there is no error or warning. So this is another mandatory check for every engineers to check the SPICE log file, because there might be some warning which can cause a potential issue. Because if you are designing a block and you will be using it in a bigger design, if something remaining as a warning at a bigger block when this block is used as a sub block, it can lead to a error. So you have to be very much clear so that no error or warnings remaining. You have to clarify everything and do the rectification accordingly. And since we do not have any error here in the SPICE output log, we can say our circuit is fine. Voltage levels are also very good in the output waveform. So we have done the construction of the CMOS circuit here using the monolithic MOSFETs, the CMOS structure, that is complementary MOS structure, where we have kept the double the area for the PMOS with respect to the NMOS, and we have encountered one typo error which we have rectified through the SPICE deck, which was not visible in the schematic. Only it become visible when we have scrutinized the SPICE deck. So this is the importance of scrutinization, checking thoroughly before you have the actual simulation. Otherwise, you have to go ahead and come back and you have to do a lot of iteration to find out the error. We're done for today. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that in the comments in the comment section down below. And bye for today.